Yeah, hi everyone. Thanks for the kind introduction. And thank you for joining our talk. So in this session, we are going to be talking about queryable state. And that's Konstantin and myself, we work for TNG, which is a consulting firm based in Munich, Germany, focused on high-end information technology. And we too are currently focused on distributed systems as well as real-time processing. So we work for a client who is one of the largest telecommunications providers in Europe, where we have built a platform that's processing billions of events per day. And we are doing this using Flink. So we're running Flink in production for 1.5 years and counting. So what are we going to be talking about today? So I've already told that to you. It's about queryable state, which is a new feature in Flink 1.2. So we want to introduce what this is. Then we want to share a use case with you that we implemented using queryable state, which is a billing system. And then the largest part of this talk will actually be a live demo of the system. And just to reiterate the scope of the talk, we don't want to get into too much of the technical details around the implementation of queryable state. If you are interested in seeing code about that, Ufuk is giving a talk after lunch, so you should head there as well. And for performance benchmarks and the like, we refer to, there's a talk on SlideShare by Stefan available, I think. So let's start. What is queryable state and why would you need something like that? So for the following few slides, just imagine a system with two kind of competing requirements. So on the one hand, you want exact, correct results at the end, but on the other hand, you also need to be able to generate real-time, low-latency insights. So a typical use case could be some system that's processing events. And at the end of the day, you want to make sure that you have the correct number of processed events that were flowing through the system. But also, every 5 minutes, you want to have the same information. What were the last 5 minutes events? So traditionally, when people solve problems like this, they use the dual architecture. I think also in one of the keynotes, you saw a similar picture. So in this Lambda architecture kind of thing, you have a speed layer that really can't be trusted. I mean, it gives you fast previews on the data, but it doesn't guarantee you any kind of correctness. And then something like a MapReduce job would run once a day and give you the final correct output. So it's obvious that this is somewhat of a duplication, right? You have operational complexity because you have to keep up those two kinds of systems. Maybe you even have to duplicate your business code for these two separate frameworks. So what fault-tolerant stream processors like Apache Flink enable you to do is basically do away with this batch layer. So coming back to the simple use case, Flink could just aggregate events up each 5 minutes and then write them to an external key value store. And you could definitely get all your delivery guarantees that you need in case that the queries are idempotent to the store, right? So, but then one could think or ask themselves, no, why do I need this external key value store? I mean, I have to operate this, I have to scale it independently of everything. And Flink, in order to give this strong consistency guarantees, has to handle the state, right? So why don't we ask the stream processor for the state we're interested in? And that's basically what the feature queryable state does. So Konstantin is going to tell you a little bit more about how this is implemented in Flink.
Yeah, right. So basically, you have 3 parts which take part in this this feature. You have the 2 main components of Flink cluster, the job manager and the task managers, and you have the queryable state client, which lives outside of the Flink cluster. So in Flink, all the state is, well, it's coordinated by the job manager, but it's the actual handles are with task managers. So either the state is actually also saved in the task manager in the heap, or it's in RocksDB. But to get the state, you actually have to
maybe step here.
So to actually get this state, you have to ask the task manager directly. So when the queryable state client wants these counts, for example, for the 5-minute windows, it has to ask the right task manager. And since you probably have maybe hundreds of task managers, not in our case, but there are apparently use cases, the queryable state client needs to know which task manager to ask. And this information it gets from the job manager with this key value state location lookup service. I think that's the name, yes. And so it asks the job manager where does this particular state element live, and then asks the task manager directly for the value. So that's actually pretty straightforward. So now the queryable state client only needs to know who the currently active job manager is, because only this job manager will have will receive all the updates of the task managers on where which state lives. So there's also a leader retrieval service in the queryable state client, which is called whenever there is a high job manager high availability failover. So then the queryable state client knows which is the active job manager, asks the job manager for the location of the state, then asks the task manager for the actual value of the state. Yes, that's basically all it is. This update between the task manager and the job manager is built in or is integrated with the normal ACA coordination between the job manager and task manager. It's just one message type, which basically tells the job manager, I have a new queryable state, or I don't have this queryable state anymore. Right, so let's get to our use case. So this use case is basically inspired from a review we did for a different project at our current client. And it was a couple of months ago, and it was implemented completely differently, obviously, because there was no queryable state, and also right now it's probably not production ready. So it was implemented differently, but when we stumbled across queryable state in Flink, we were like, okay, this fits perfectly, and we just want to prototype it in Flink and see how it works, just to try out this new feature and get some experience with it. And actually this project is kind of revived now, and there are a lot of new requirements which also call for queryable state, in my opinion. So it might actually be that they will rewrite a good part of it, and they are already using the dataset API. So they might actually switch to something like we are presenting right now. Okay, what were the requirements? It's basically you have network events which are indicating usage. It could be data usage from your phone. It could be texts, calls, additional package you're booking. And those are billions of events coming from the network. And this system basically needs to tell the invoicing system what is the total amount due at the end of the month. And this needs to be correct, of course. And this is basically the main use case, just adding up these billable events, let's say. And then there is this side use case on the bottom that you want to expose the current usage to the user so that he can check in a maybe mobile web app what's the current usage during the current month. And yeah, you could also think of additional dashboards which give management real-time insights into the customer behavior to target advertising campaigns and so on. I mean, there's a lot of, you can imagine a lot of stuff. But what we will focus on is the main pipeline in the middle and the pipeline towards the user. So what are some important quality goals we have there? There's correctness. That is the most important one. You want these bills to be correct. If they are too high, customers will complain. If they're too low, you will lose money. Actually, you will use money in either way. But yeah. Then there's also robustness. You have a lot of, well, out of orderness in these events. You have a lot of late events because the source is very heterogeneous. So you have a network which is spread over a large area, and you will have different delays. You will have partial failures of the network where they are cached at some network component. Yeah, we're also experiencing this in our current project for different use case. So, and of course, in a distributed system, you will have partial failures. So this is the other kind of robustness you need. Then there's also availability, which is not so much of an issue if you're just looking at the monthly bills. But once you have the stream processor also serving those queries, you also want it to be available for most of the time, at least. And scalability, well, it's always kind of requested if you have a system which processes a lot of data and you're not really knowing where you're going with it. So in this case, it could be that the network elements start generating a lot more events. That's actually happening because of changing network topologies and stuff like that. But you also have a lot of scalability also helps elasticity over the day if you have very different amount of data during the day. So this is basically the requirements, and Max will go a little bit into how we implemented it.
Sure. Let me just quickly tell you in terms of technologies, how did we try to solve these problems, and how did we build this prototype. So from the left-hand side, you see there are these network events coming in. We buffer them in Kafka. And then there's an Apache Flink job, basically the core part of our application, which then writes out, I mean, does some windowing, aggregation, we get to that, but it writes out the invoices into a distributed file system from where then the final invoicing system that actually sends the bills out to customers could fetch these bills, right? So this is, yeah, for the purpose of the demo, you could, of course, also think that this invoicing system on the right-hand side just accepts HTTP calls of an idempotent manner. But we did it this way, and notice, so this combination, when you have a Kafka source and a, let's say, HDFS sync or distributed file system sync is one that enables you to do exactly once, right? Because you can, in the event of failures and you want to restore state, you can, on the one hand, rewind your Kafka sync to the exact point, and you can also truncate in your distributed file system. So we don't have any duplication in the output. So yeah, that's the main, let's say, bill or invoice generation part. And then on the bottom, we wrap this queryable state client in a small Spring Boot application, which exposes somewhat RESTful interface to a mobile web application written in JavaScript, and then also something that we aren't going to show, but it's basically functionally exactly the same, would be this management dashboard, which you could do in tools like, say, Splunk or Grafana. So zooming in on the Flink job, it's no rocket science. I mean, the job graph doesn't look very spectacular, right? So on the left-hand side, we get the events from Kafka. We assign timestamps, insert watermarks. If you joined the advanced training yesterday, you know all of this already. So this is the blob on the left-hand side. And then on top, the logic is to do time windows. Right, so monthly time windows in this case, where we then fold up the state. So in particular, we key by customer and add up all the amount for this customer that should be billed to him. And then there's a bucketing sync in the end. Now, what you would like to do with this is now in this time window expose your queryable state because you already have it there. Unfortunately, this is currently not possible. Because you cannot expose a state in Windows currently. So what we built kind of a workaround. We duplicated the whole structure with your time windows and the aggregation strategy, and just trigger on every event. And then in the window function that gets triggered, all the time we expose the state. This is a current limitation which should be solved pretty soon, if I understand correctly the data artisans. plans. So okay, and yeah, just to make it clear, this is the second blob on the right-hand side, and then the third blob is basically the same with a different kind of aggregation. So in this case, we key by event type. So is it a call, is it a message, whatever, and then expose this. So that's a job graph. No rocket science, as we said. Now, we also said we want to be robust against failure scenarios that we are going to show you in just a moment. And to do that, it's also no rocket science, right? You just use whatever Flink gives you. So we enable checkpointing. We use a RocksDB state backend, which is the recommended thing for many use cases. And we use Zookeeper with jobmanager high availability. Right. So let's start.
Yeah, let's start with the demo. I will actually step down because I have to see what's going on the screen, because it's not completely deterministic. So yeah, there's some random data coming in. So okay, let's have a quick look again at our list of requirements, because we will kind of check them during the demo. So we have these functional requirements, which are basically the invoice generation and the live updates, which should be queryable. Then we have some quality goals, correctness and availability. We won't look at scalability because it's just a local setup and there aren't that many keys. Just doesn't make sense in this context. And then we have robustness, and there we have a list of things we want to look at. We want to see that it's robust to late events, to task manager and job manager failures, and also to failures of the downstream system. So basically the Flink sync. Okay, so let's first have a look how we set it up. It's basically a Docker setup with a couple of containers. Can you even make it a little bit larger?
Can people read it? No.
Okay. So, is this readable?
Somewhat, yeah.
Okay. So we'll see. We need a few more terminal windows throughout the demo. So we'll see how it works. So we have 4 containers which make up the Flink clusters, 2 job managers, 2 task managers, so that we can kill one of them later. We have 1 Kafka broker, that's the third one, and on the bottom we have Zookeeper for both job manager high availability and Kafka. And then we have 4 containers for this queryable billing application. For once the QB job, that's just the Flink client which submits the job to the cluster. Then we have a QB server, that's the small Spring application wrapping the queryable state client, and then we have the data generator, which just writes continuously to Kafka, and the front end, which just statically serves the web application. You'll see in a minute. Okay, so let's start with the invoice generation. So I think that's not readable now, but we have a little bit space. So
this one a bit larger, maybe.
Yeah. So let's first have a look at the data that's generated by the data generator. So it's in this window. So there are a lot of events coming in. They have an event timestamp. They have a name. It's only 9 names. I think the most popular baby names in the US of the last couple of months. Then there's an amount and there's a message type. The message type is completely random. The amount is a little bit random, so the timestamp is random and the individual amounts are random, but they always add up to the same sum for each customer in each month. So we'll later see when there are failures, because it always has to be an even amount. You see the job running on the top for 59 minutes now. That's why we're in 1979. We started at the epoch. Okay, so let's just keep it running on the left. Right, and we'll have a look at the distributed file system. Distributed file system, you didn't see any like HDFS containers or anything, so the distributed file system in our case is just a Docker volume mounted to all the containers, which kind of simulates the distributed file system. So, and that's basically in the middle. So we see we have 1 folder for each month, and they contain the invoices. So if we cut on all those files, you basically see, okay, last month was April, and you see all all the final sums. They're all even, which kind of indicates there was no failure. There's one uneven in January, and that's a late event actually. So there are some late events which are later than 3 days in the data, and then the bucketing sync will already fire with the data that's available after the month and the bounded out of orderness, which is 12 hours, and then it's fired again once the late event arrives. And there's, I think it's a couple of lines below. It's the updated results, so 2 lines below with the even 200 then. And that's something the billing system or the invoicing system, the downstream system has to cope with. Otherwise, it's just not working. Then you can also use just longer out of orderness. Yeah. Okay, so I think invoice generation works. It's correct in case everything goes right. We also saw late events. There's also just normal out of orderness going on all the time, which is a little bit harder to demo now. Okay, so let's look at the live updates. We said where there's this web service which makes them available, so we can just curl it. So this was, for example, a call on the type call. You can also call message. And let's call one of the customers. Let's call Emma because she has even 100 at the end of the month. Yeah, it's 88, it's 95, then at some point it's 100, and then it will start in the next month, basically. I hope it's at least somewhat readable. Okay, but we to now continuously see if this is working, the queryable state is working, we have just this small web application which queries the amount for a couple of the customers.
Right, yeah.
So what it does every 2 seconds, it just asks for the current amount in the month. And let's take Emma and Isa. I think there. And the green color indicates that it worked. So it will turn red in case of that the Flink cluster is not answering the Spring Boot application. So now we have like a nice setup to check what happens in case of job manager and task manager failures. And that is actually the next thing we're going to look at. Live updates is getting a check. And yeah, let's look at task manager failures. So we can just kill the Docker container running one of the task managers, and let's just see what happens. Okay, we see Emma, it was served by this task manager, so it immediately doesn't work anymore, and that's what you would expect. Isa still works because the other task manager doesn't know that the other task manager died. And it is told so after the akka timeout, basically by the job manager, and then this also doesn't work anymore. So you kind of see this direct link between the queryable state client and the task managers. So now the job manager is failing. We don't get any invoices anymore, I guess. So we are in December now. And what was the last invoice? Actually, we're still up to date, but we will not generate any more invoices now. And the job cannot come up because we're running with a parallelism of 6, and we only have 4 task slots still available to give us a little bit more time. So, of course, in a production setup, you wouldn't build it this way, that the job just dies once one task manager is gone. Okay, but it gives us a little bit more control here. So let's bring this task manager up again. So you see starting task manager 1. Now the job should be restarting, and the updates should work again. Emma is working. What about Isa? Isa is working too. Okay. All right. So now it's just fast forwarding through Kafka, and basically the 2 months for Emma and Isa are just much faster than they originally would be, and we can also see that we have correctness in the output because there are only even numbers. There's 199, but that's allowed lateness again at some point, and there's but that was before the failure. November was before the failure. Yeah. So task manager failures work with exactly once, and so that's the check for robustness. Availability is somewhat compromised. So as long as your job is not running, you won't get any answers of the queryable state servers or the key value state servers. Okay, let's look at job manager failures. I will talk about availability at the end, a little bit longer. So let's just kill the job manager, which is actually the active one.
True.
Yeah, okay. So we killed the job manager. So job manager is gone, but it still works because they have cached the location and they're going to the task manager directly, and the task managers don't know the job manager is gone. So that's still working. But at some point, the task managers will realize that the job manager is actually on, and they will also be killed, and the job will be restarted. And at that point, we'll see it in a second. There will be a downtime for the key for the queryable state too. So we have these two bookmarks up there. Yeah. Okay. Now the failover has happened, and there's no job right now, and so the updates don't work anymore. Now it just takes some time for the failover or for the restart of the job. There it is. Now the queryable state client is told about the new leader, and it gets the new location of the newly distributed key value state, and it works again. So let's also have a quick look at the invoices, if everything went right there. Okay, there's some folder, but yeah, it looks good. All months are there, all even amounts. Yeah, not even any lateness in that part. Okay, so job manager failures also work pretty nicely. There's again this small availability gap, but it's not as bad as with the task manager failure, because actually the amount between the task managers realizing their job is gone and the restart is not that long. Okay, let's have a final look at failure of downstream systems. Two things about that. First of all, what is the downstream system in our case? It's basically the file system, so we will make the file system unavailable for the job. And the other thing is what would actually be the desired behavior. And we think it should just stay, everything should stay in Kafka, and we should build the backlog in Kafka, because Kafka in these kind of applications is always the fallback layer, which has the persistence and which we can replay from. So we would hope that the job just fails and everything will stay in Kafka. So we're just moving this invoices folder to invoices archive. And then we can have a look what's the last month in the invoices archive. The job is still running because it doesn't have to write out right now. So, but it will fail once it tries to write to the disk. So now it's failing, and now it's getting stuck in a failing restart loop, because it starts up, then it pretty quickly wants to write out again because it's replaying from Kafka pretty fast, fails again. Okay, now we can and you can also see, okay, the queryable state client, it has some moments where it's live, but it's basically failing all the time. So let's just recreate this invoices folder. And now the job should actually keep running. Yeah, looks good. Let's also have a quick look at the invoices. So the last month in the archive was August. So we would expect, that's a nice effect there. There's September, and the next month is November now. Actually, we didn't lose any data, but we're using 30 days windows because there is no native support for month windows. And by now 1980, there is some skew. So
you have to appreciate how cool it is that we matched exactly this moment in time for the demo.
Yeah, it's
very nice.
Yeah, actually, we didn't want to tell this. Because we wanted to implement month windows, and we didn't have the time, so we had to go with the 30 days windows. Okay, but in general, it works. But availability is is impacted again. Every time the downstream system is not available, the Flink job will not run, and your queryable state will not be queryable. So that's all we want to show. Let's wrap it up. So we could see some current limitations in the queryable state. So first of all, there's no support for window scoped queryable state. So it's only the key, and as I learned yesterday, the window is actually the namespace. So there's no namespace support for queryable state, but this will be added shortly. Then the client API is somewhat cumbersome. You have to deal with all the Flink serialization in the client, and well, it's not as nice as, for example, Elasticsearch's API. I mean, it's not what you would expect at that point, but they will definitely need to improve this to make it more easily applicable from different kinds of clients. Then there's state size. So I'm not sure how well this will scale if you have queryable state of like hundreds of gigabytes, or we haven't tested it, but I have a doubt that Flink right now is like beating full-grown key-value state or key-value databases when it comes to really big queryable state size. And last but not least, the availability in case of job failures. So Stefan was talking about this partial recovery thing for jobs yesterday, and I think this might help there. So the idea is that you basically, in a case of failure, you only recover this part of the job which needs to be recovered, and this could help here because then only if your queryable state is in this part which needs to be recovered, then it would not be available, or at least potentially you could build it this way. So this could become better, but right now it's definitely limitation because you're completely coupling your processing and your latest updates, or the availability of your latest update. Yeah, so that's all we wanted to say. If there are any questions, we're happy to take them, and have a nice conference.
If you have any ideas of scenarios that we could try to tweak through, please feel free.
When a task manager fails, but you do have enough available slots, will there still be downtime like we saw, or will it recover quicker?
Okay. The question was whether task manager or the recovery in task manager failure is quicker if there are enough slots. It's definitely quicker because it can restart right away. But in our scenario, it depends on a couple of timeouts, but in our scenario, it would still be 30 seconds or something like that. Yeah.
I've got two questions. The first one is, how do you handle duplicating message? Because you are building an invoice system, and if your network is inconvenience, and there's some event may duplicating, and in this kind of invoice system, how do you handle duplication? Because in the offline, you can always try to kind of dedupe.
Yeah.
That's the first question. The second question is, since you co-locate the query message with your computation resource, and in the case that if you expose this query API to the outside end user, and there's a lot of high QPS kind of requests come in, will that be impact your computation engine interpretation tool? And what kind of use case will be applied this open this API to the end user, to the end system?
Yeah, good questions. So the first question was, how do we deal with duplicated events which are coming into the system? So if they're already duplicated in Kafka, we're not. And so in this case, we're not dealing with them. And it's actually a very good point, because in a full pipeline, exactly once is super hard to achieve. And yeah, it's definitely a limitation of this POC at least. Yeah. The second question was, if you expose this API to the outside world, to the end user, then you don't really control the load, and you're coupling it with your stream processor. So basically, they're competing about resources. So it's one of these performance issues which we didn't really have a look at. So there is a talk by Stefan who is exactly, I think, looking at the scalability of queryable state in both dimensions. Once the number of keys which you have the state for, because this will of course be much more than 9, which it was in our case, but also on the query load. And if I remember correctly, it performs pretty well. But yeah, maybe just grab Stefan later and ask him about it. Stefan Evan. Yeah.
That's a question at the back. The thing is, if I understood your question correctly, you said in an offline processing situation, you would be able to deduplicate. Basically, using time windows, as long as they aren't super late arriving events, you can do the same business logic for deduplication inside your Flink time windows, right? So
you couldn't
so
fold.
Exactly what he's saying.
Yeah,
right?
Basically, as long as you have enough memory to keep everything in state, or if you're using RocksDB, as long as you have enough disk to keep everything, all events for this 1 month and the allowed lateness, then you can just deduplicate in the window. But the way we did it with a fold window, we are not keeping every, we're summing up directly. So in this implementation, it wouldn't be possible to deduplicate it, but as long as your throughput allows you to use RocksDB and you have enough disk space, then you could do it. Yes. Yeah, the question was basically why you can't just duplicate based on an event ID or something like that. Yeah. Right. Yeah. Yeah. Yes. Basically, this bucketing thing, which is just a file thing, which writes into different buckets. In our case, a bucket is a month. That's the folders. It's basically has a rollback mechanism in case of failures, or when a checkpoint is restored, it's truncating to the last checkpoint and keeps as a checkpoint the byte offset in the file until Flink, or to the point where Flink knows that was correctly checkpointed, and I'm gonna jump back to it. Yeah. So this bucketing thing isn't exactly one thing. It's kind of transactional in some sense. Yeah. And yeah, but there are other options for sync, because probably in a corporate system you wouldn't use this file system. I mean, of course you wouldn't use a Docker volume, but that's a different story. Yeah.
So you talked about you had a typical sinks there, but you didn't talk about sinks.
Yes.
And particularly when you're chaining multiple jobs, how do you really get the exactly one guarantees, and what are you doing for that?
Okay, so the question was, Max mentioned that there were other possibilities to have an exactly one sync besides HDFS or the file sync. So what we basically thought of is kind of a put on an HDFS put, which the HTTP, sorry, which the invoicing system handles idempotently. Then you basically have an exactly once semantic. But with this exactly once, it's always either you have the latency or the downstream system has to deal with it. I mean, I don't think there's another way. Either you add latency and the downstream system also waits for allowed lateness, but then you don't need allowed lateness, then it's just out of orderness. Or the downstream system can deal with, or can process the events idempotently. And if you have neither, then you can't achieve out of orderness. Otherwise, only if you have a transactional thing, but then again, you have to wait. So it's not really solvable in a general way, I think. What do you think? I didn't get it, sorry.
So we announced a new product called Pravega today morning, right? We're going to have a session about it later on.
Yeah.
That kind of helps you with this problem.
That's nice. Yeah. I will definitely go to this session. So everyone go to this session. All right.
So enjoy your lunch, everyone. Thanks.
Thank you. Bye-bye.